All right, welcome to chapter 5.4 of our calculus book. And 5.4 is about modeling and optimization. I mentioned this before, but really modeling and optimization is one of the major uses of calculus in real life, because obviously we want to optimize things to the greatest extent possible. Going to be heavy on problem solving in this section. I'm going to talk to you about a strategy, steps of the strategy. Not every step will apply to every single problem, but I'm going to be referring back to it. So I'm going to go ahead and bring this up on the next screen. What I'd recommend that you do is pause here, take a quick snapshot of this strategy, and just store this somewhere. As you are working through problems, if you get stuck, go back, take a look at the strategy and say, okay, did I work my way through each of these? Did I do that? Did I do that step? And it may be that at times you'll discover that, in fact, oh, look, there's a step that I needed in order for this to make sense. So let's take a look at a problem, and I'll go ahead and I'll sort of walk you through step by step on that strategy. And the problem is this: I want to find two numbers whose sum is 20 and whose product is as large as possible. So step one, read carefully, identify the information. So let's go ahead and take a look at this. Thing one, two numbers. Okay, fair enough. The sum is 20. That seems pretty important. Product is as large as possible. So I've got three pieces of information that are going to be useful there. And let's move on to the second step. Draw pictures, label the parts that are important to the problem. This is not really a problem that pictures, I think, are appropriate. So let's move on to the next. Introduce a variable. Well, let's call number one x. And since I know that number one is x, I know that the second number must be 20 minus x. This is the sum is 20 part. And now, using the variable, write a function whose extreme value gives the information sought. Product. So what is the product? So step number two, we're still in step number two. I could label that down. I won't normally, but the product equals x times 20 minus x. And so I'm going to call this P of x, for product of x is 20x minus x squared. And my goal is to maximize this. Graphing the function, find the domain, determine what values make sense. So I'm going to say, looking at this, that probably, I mean, we've got a quadratic here, but if I look at this quadratic, it makes sense to me that the maximum is going to be between 0 and 20. It's a downward opening parabola, and I mean, I already have a pretty good idea of where that maximum is, but I'm not going to worry about that yet, because the point here is the steps. So I'm going to say that I'm just going to look at x values between 0 and 20. All right, critical points and endpoints. Okay, so endpoints, we've got x equals 0, x equals 20 based on my domain. Critical points, well, p prime of x equals 20 minus 2x. I want to know when this equals 0, and I get that x is equal to 10. And there are no places where the derivative doesn't exist. So the three things that I'm interested in are my two endpoints and my one critical point. Solving my mathematical model, I'm looking for a maximum. So I'm going to find P of 0, which is 0. I'm going to find P of 20, which is 0. And I'm going to find P of 10, which is 100. And therefore, this is a maximum. So my two numbers, going to the final step. This was step 5, by the way. This was step 4, finding those critical points. And step 6, the final step, is translate your mathematical result into the problem setting and decide whether the result makes sense. Two numbers are 10 and 10. And yes, that makes sense. They are within my domain. 10 times 10 is 100. It is a large product, and if I wanted to do a few in my head, I'd see that 19 times 1 is 19, 1 time, et cetera, et cetera. So this seems like a pretty trivial example. You probably didn't need to go through all these processes to find it. Honestly, we didn't even need calculus to find it because we're looking for the vertex of a parabola. But I think it's pretty illustrative of what we're trying to do when we talk about the strategy and how the steps help us out. Okay, so my class, why don't you go ahead and do exercise number 1 in section 5.4, and we will come back with a new problem. So example 2, inscribing rectangles. And there's some pretty famous math problems that involve inscribing rectangles. What we're going to do is we're going to look at a not famous math problem that I'm aware of, but we want to just inscribe it under one arch of the sine curve. And we want to maximize the area of the rectangle. So, step 1. Let me go through. First off, I've got an arch of the sine curve, and I want a maximum area. I think that's probably everything I need to know. I'll have to pull some information out of my head about sine curves. Let's draw a picture. Here we go. Here is a sine curve. We've got one arch of the sine curve. And so I'm going to label this pi over. No, I'm not going to label it pi over anything. I'm going to label it pi. I know that that's a maximum of 1. I'm going to go ahead and draw myself a rectangle that is underneath the arch of the sine curve. You'll notice that the problem doesn't say that the corners have to touch the sine curve, but of course it wouldn't be a maximum area if they didn't touch. So, and let's see what comes next. Introduce a variable to represent the parts of the problem. Well, I'm going to go ahead and I'm going to call this point P, and I'm going to call this point Q. And I'm going to call this distance x. And the reason I'm going to call that x is because then I know that the coordinates of point P is x comma sine of x. And I know that the coordinates of point Q is pi minus x because of symmetry, and that it has the same height, sine of x. So the length of this rectangle right here is pi minus 2x, And the height of the rectangle is sine of x, which means that my equation, a of x, is pi minus 2x times sine of x. Step 2, draw a picture, label the parts, introduce the variable, write a function whose extreme value gives the information sought. And since I'm looking for max area, I want a function of area. And so I'm ready to go. Graph the function to find the domain of the function. So when I graph this, the graph of this function, and I don't have my calculator right with me. Where I just ruined this video because I just showed you. I'll clip that out later. So if I graph this function, what I discover is that this function actually, from x equals 0 to pi, does actually look something like that. So again, I'm going to say that the domain of x, the bit of the graph that I'm looking for, needs to be somewhere between 0 and pi, which, you know, did I need to draw a new graph of the area model in order to find this? No, I could have looked at my original graph and said, oh, look, it goes from 0 to pi. Okay, so let's take a look. And our next step is to identify critical points. Well, endpoints are at x equals 0, x equals pi. I can already see that the area of 0 is equal to 0, and that's also the area of the rectangle at x equals pi. My critical points, let's find the derivative of the function. So I'm going to use the product rule here. So I'm going to call this u, I'm going to call this v. U dv is pi minus 2x times cosine of x plus v du. Derivative of u is negative 2 times sine of x. And I need to know when this is equal to 0. So I need pi minus 2x cosine x minus 2 sine x equals 0. That's a 2. And I've got a little bit of a problem here, is that I can't solve this algebraically. There's an x term here, there's a cosine and a sine. I could divide everything by cosine and I would get tangent, but I'd still be looking at when does a tangent function equal the input function of the input value. So what I'm going to have to do in this case is I'm going to have to solve this algebraically, or excuse me, I just said I can't solve it algebraically. I'm going to have to solve this graphically. And when I type A prime into a calculator, what I get is I get a function that looks something like this. A prime is equal to 0 when x is approximately 0.710. So what I know is that the dimensions of my rectangle will be pi minus 2 times 0.710 by sine of 0.710, and my maximum area, which is what I'm trying to find, will be about 1.122 square units. So thinking back on the steps, I sort of whizzed through a few steps. We identified, this was step number 4 right there, identify the critical points and endpoints. Number 5, we solved the mathematical model. which, having identified the critical points and endpoints, was the step here where we found the x and we came up with the dimensions. And step number 6, interpret the solution. Remember, it's not good enough to say x is 0.710. We need to say the area of the rectangle is with dimensions of, and that helps us make sure that the answer makes sense. It would be very easy to come up with some value of x and just write it down, having made a mistake, and discover that my result makes no sense when I phrase it in terms of a result. Okay, so my class, go ahead and do exercise number 6 in section 5.4. I'm going to stop this video here. I'm going to do another exploration in the second video, but it's fairly long and complicated, got some interesting algebra in it, so I just wanted to make it its own video. All right, thanks for watching.